Why C still matters in the age of Python and AI. Welcome back to Gate and Kernel. Today, Python dominates programming education. AI can generate code in seconds. Modern languages give us powerful libraries, automatic memory management, and high-level abstractions. So a reasonable question is, why should anyone still learn C? C was created more than 50 years ago. It has no classes built into the language. It has no garbage collector. It does not protect you from many memory mistakes. And compared with Python, writing C often requires more work. Yet C is still everywhere. Operating systems, embedded systems, device drivers, compilers, databases, networking software, and many of the technologies underneath modern computing. So C is not important simply because it is old. C is important because it gives us something many modern languages intentionally hide: a relatively direct view of how software interacts with the machine. 1. Modern programming hides the machine. Consider Python. If you write x equals 10, you normally do not need to think about exactly where that value exists in memory. You do not manually allocate space for it. You do not usually ask which CPU register contains it. You do not worry about freeing the memory afterward. Python handles enormous amounts of complexity for you. That is one reason Python is so productive. It allows programmers to think about the problem instead of constantly thinking about the computer. This is a major advantage. But it also means that much of the machine is hidden. C works differently. C exposes more of what is happening underneath your program. And that is why learning C can change the way you understand computers. 2. C makes memory visible. One of the biggest differences appears when we talk about memory. In C, variables are not just abstract names. They occupy memory. And every location in memory has an address. For example, int x equals 10, the variable x contains the integer value 10. But x also exists somewhere in memory. C allows us to ask for that address. Using a pointer, we can store it and work with it directly. This introduces one of the most important ideas in systems programming: a program does not simply manipulate values. It manipulates values stored somewhere inside the computer. Once you begin working with pointers, arrays, structures, and dynamically allocated memory, concepts such as addresses become much more concrete. You start asking questions like, where is this data stored? How many bytes does it occupy? Who owns this memory? When should it be released? What happens if I access the wrong address? These questions may make C more difficult. But they also reveal how computers actually manage data. 3. The stack and the heap. C also gives us a useful path into understanding the stack and the heap. Suppose a function declares a local variable. That variable will often live on the program stack. If the program dynamically allocates memory using functions such as malloc, that memory usually comes from the heap. These two regions behave differently. Stack memory is normally managed automatically as functions are called and return. Heap memory can remain allocated until the program explicitly releases it. This is why a C programmer needs to understand functions such as malloc, and free modern languages often manage this automatically. That makes programming safer and easier. But C forces us to see the mechanism. And once you understand that mechanism, many other programming concepts become much easier to understand. 4. C is close to machine instructions. Now consider a very simple C statement: C equals A plus B. To us, this looks like one operation. But the CPU does not execute C directly. A compiler must translate the program into machine instructions. Conceptually, the processor may need to do something like this: load or access the value of A. Load or access the value of B. Place those values where the processor can use them. Perform an addition. Store the result in C. At the assembly level, that operation may eventually involve an instruction such as ADD. And now we arrive at the hardware. The instruction identifies the source data. Values are read from registers. Those values travel into the arithmetic logic unit, or ALU. The ALU performs the addition. The result is then written back. So this simple C statement, C equals A plus B, can lead us through several layers: C source code, compiler, assembly or machine instructions, registers, ALU, and finally, electrical logic inside the processor. This is one of the reasons C fits so naturally into computer architecture. C is high-level enough for humans to write useful programs, but it is low-level enough that we can still see the machine underneath it. 5. Why operating systems still use C? This relationship with hardware is especially important in operating systems. An operating system kernel must control resources directly. It manages memory. It handles processes. It communicates with devices. It responds to interrupts. It works with CPU architecture. And it must often operate with very little overhead. This is exactly the kind of environment where C is powerful. C gives programmers relatively direct control over memory and data representation while still providing structured programming features. This is why so much system software has historically been written in C. The Linux kernel is the most famous example. But the larger lesson is not simply that Linux uses C. The important point is that operating systems live very close to hardware. And C was designed for exactly that kind of environment. 6. C is everywhere underneath modern software. Even if you never write a large C program yourself, you may use software built with C every day. Programming language runtimes, database engines, networking libraries, operating systems, embedded firmware, device drivers, compilers, and countless system libraries contain C or interact with C interfaces. This creates an interesting situation. A programmer may spend an entire day writing Python without writing a single line of C. But underneath that Python program, many important components may still depend on lower-level native code. High-level languages did not eliminate systems programming. Instead, they built additional layers above it. 7. C versus Python is the wrong question. This is why asking whether C is better than Python is usually the wrong question. They are designed for different purposes. Python tries to remove unnecessary complexity from the programmer. C gives the programmer much more direct control. Python is excellent when development speed and readability are important. C is excellent when memory, performance, hardware access, or predictable low-level behavior matters. Python says, "Let me handle many machine details for you." C says, "Here are the machine details. You can control them." Neither philosophy is universally better. They solve different problems. A good programmer can understand why both approaches exist. 8. What about AI? Now we have another layer. Artificial intelligence can generate code. You can describe a program in natural language and receive working Python, JavaScript, C++, or C code almost immediately. Does this make learning C less important? In some ways, AI reduces the need to memorize syntax. But understanding becomes even more important. AI can generate a pointer. But you still need to understand what the pointer points to. AI can call malloc. But you should understand what memory is being allocated. AI can produce multi-threaded code. But you still need to understand race conditions and memory safety. AI can generate assembly. But without understanding registers and instructions, debugging that output becomes much harder. The easier code becomes to generate, the more valuable it becomes to understand what that code is actually doing. 9. Should beginners still learn C? Not every beginner needs to start with C. Python is often a much easier first programming language. It allows beginners to learn variables, loops, functions, algorithms, and programming logic without immediately dealing with memory management. But after learning basic programming, C can be extremely valuable. C exposes concepts that high-level languages often hide. Memory addresses, pointers, data layout, the stack, the heap, compilation, machine instructions, and the relationship between software and hardware. You do not need to become a professional C programmer to benefit from learning these ideas. Even a moderate understanding of C can make operating systems, computer architecture, networking, compilers, and performance much easier to understand. 10. From programming to the machine. This is the real reason C still matters. C occupies an important position in the computing stack. At the top, we have applications. Below them are programming languages and libraries. Below that, operating systems. Below the operating system are machine instructions. Then registers and the ALU. And underneath all of that are digital circuits built from logic gates. C sits close enough to the lower layers that we can follow this path. A line of C can become an instruction. An instruction can move data through registers. The registers can feed an ALU. And the ALU ultimately performs operations using digital logic. Once you see these connections, programming stops being isolated from computer architecture. The entire computer starts to become one connected system. Conclusion: C is old. But old does not mean obsolete. Modern languages such as Python make programming easier by hiding many low-level details. AI makes generating code easier still. C remains valuable for almost the opposite reason. It exposes many of those details. Memory, pointers, data representation, compilation, machine instructions, and the connection between software and hardware. Learn Python when you want to build things quickly. Learn C when you want to understand more of what the computer is actually doing. And once we move below C, we enter an even deeper world: assembly instructions, registers, the ALU, the operating system, and the kernel. That is the world we explore at Gate and Kernel.